Hello everyone. In this video, L8-2, we are going to cover implementing a hash table in Python. In the previous video, we covered L8-1, where we went over a high-level overview of what a hash table is. We worked through a few examples of putting items into our hash table and retrieving items from our hash table. We also talked about a simple method for implementing a hash function that was called the remainder method. And we also talked about how to handle collisions in our hash table with two different approaches, linear probing and chaining. Now, the learner objectives for this lesson include implementing a hash table with collision handling. The collision handling we're going to use is linear probing, and also introducing the map abstract data type. And we will implement a map that will have similar functionality to a dictionary in Python. So let's take a look at an implementation of a hash table. So here's our class hash table. Let's take a look at the constructor. So by default, we're going to set the size of our hash table to be 11. This is going to be quite small. In fact, hash tables are usually much larger than this, but we want to strive to have our hash table sizes be prime numbers, because in the case of the remainder method, for example, when we mod by a prime number, this is going to reduce the clustering in our table. The second line of code here in our hash table constructor is going to declare a list of self.size items, so m items, and each item in that list is going to initially store none. So essentially, we're going to use a Python list as our underlying data structure for our hash table, and we'll store that reference in an attribute called slots. And just as a reminder, this here is the list repetition operator. So we're going to repeat the singleton none self.size number of times. Common operations associated with hash tables include put, get, and remove, as well as code related to our hashing and collision handling. So put accepts an item and attempts to place an item in the table. If it is able to successfully place the item in the table, then the slot number will be returned. Otherwise, the special flag -1 will be returned to indicate that the table is full and there are no available slots to insert this item. Our operation get is going to accept an item and return the position of this item in the hash table if the item is there. -1 will be returned otherwise. Get is like a peek method associated with a stack. It doesn't actually modify the hash table. It's just going to see, is this item there? Essentially, it's like a search. Remove is going to accept an item and remove the item if the item is in the hash table. If the item is not in the hash table, then -1 is going to be returned. These two methods down here are related to hashing and collision handling. Hash function implements the remainder method as our hash function, and rehash is going to take the old hash value, add 1 to it, and then using the remainder method, rehash in order to spread out our values using linear probing. Here's some code here that is going to exercise our newly implemented hash table. So on the first line, we're going to instantiate a hash table object. We're going to insert these items in this sequence using our put method. At this point, we're going to print out our underlying list data structure that's storing our hash table slots and the items in those slots. And we'll put 2 more items in and print out the slots again to find out that the table is full. Let's pause here. And here is the output from this line of code here. We see that there are only 2 slots open in our hash table. Then we insert 2 more items and print out the slots again to completely fill our hash table. Now, if we try to insert another item, regardless of what that item is, such as 90, -1 is returned by put indicating the table is full. We cannot insert another item. Now, this second to last line here, let's remove one item, item 55. Item 55 is at slot number 2. we print out slots after we remove 55, and now we see slot number 2 is now none, indicating that it is empty. So now we could try to insert 90 again, and since this is the only slot available in the table, regardless of what its hash value is, rehashing using linear probing is going to insert it in this position. Now let's talk about a map. Since we can implement a hash table, we can now implement a dictionary, which is an implementation of the abstract data type called a map. A map is an unordered collection of key value pairs. The keys are unique so that there is a one-to-one relationship between a key and a value. To look up a value given a key, we will use a hash table and a parallel array to store the values. When we look up a key, we will hash it to identify its slot. Then we can look up the value in a parallel array stored at the same slot location. So in the map implementation that I'm going to show next, we're going to have string keys that are going to map to integer values. So we're going to take an aside here to talk about how we can hash strings. A simple approach to hash a string is to compute an integer representing the string by summing the Unicode values for each character in the string. So for example, with the built-in Python function ord, I can get the Unicode value for a character. So the variable C is going to store the Unicode value for the letter C, and so on for A and T. Now, we can compute a hash code for a string such as cat by adding up the Unicode value for C, the Unicode value for A, and the Unicode value for T. This will be the hash code, and then to get our hash value, we'll map it using the remainder method by modding by 11. So to run this code, a simple method works, except it's going to map anagrams to the exact same bucket. So cat and tack are anagrams of each other, which means they have the same letters, they're just rearranged in a different order. So cat and tack are both going to have the exact same hash code here. Modding by 11, they're both going to map to slot number 4. In the next lesson, we'll learn about a way we can overcome this shortcoming of the anagram problem. But for now, we can talk about using a string special method called dunder hash dunder. So if we get a hash code from a string from the built-in Python functionality to do this, and then we mod by 11, we'll see that we get these hash codes that are crazy long that come from the special method hash for strings, and then we mod by 11, and these happen to map to 2 different slots. But I would like to note that by default, the special method hash values of stir, bytes, and datetime objects are salted with an unpredictable random value. Although they remain constant within an individual Python process, they are not predictable between different executions of Python. So if I were to continually run this over and over again, I'm going to get the same hash code for cat and tack. But what this means is if I were to restart my Python kernel or perhaps save my Jupyter notebook and reopen it, I'd have a different invocation of Python, and these hash codes could be different. Something to keep in mind. Okay, so let's take a look at an example implementing a map abstract data type. So we're going to have a map class that is going to inherit from hash table because we really just need to add a little bit more functionality to what already resides in hash table. So in our constructor, we're going to call hash tables constructor passing in size, and then we're going to create our parallel list called values. We initialize it the same way as we initialize slots. And this is where we're actually going to store the values this time. In the previous slots, we're going to store the keys. So I've implemented a few special methods here, a string representation, len, so we can use the built-in Python function len to get the number of items in our map, just like we would with a dictionary. Get item, set item, del item, these are so we can use the hard bracket notation that we do with dictionaries. And contains, this is going to implement the functionality for the Python reserved keyword in, which test for membership in our map. So put, get, and remove are all going to call our parent put, get, and removes in hash table, but upon successful placement of our key into our slot list and hash table, we're going to store the value associated with this key in our parallel list in the map class. So here's our hash function here, which is going to use our simple approach that I showed you earlier for summing up the Unicode values associated with a string. This is going to have the anagram problem I discussed earlier. We could replace this with the built-in string hash code from the special method hash if we wanted to. But for our small example, this is easy to debug, and we can walk through and see what's going on in our program. So let's make a new map, and we're going to add key value pairs where our keys are going to be strings, and the values those strings associate with are going to just be the number of characters in that string. So insert cat, dog, lion, tiger, bird, cow, goat, pig, chicken, and then we will print out the map. So here's the result of my stir special method. Tiger maps to 5, cow maps to 3. Remember, these are just the number of characters in the key. And we see that there are 2 open slots in our dictionary, in our map. So we can add 2 more, and then the hash table is going to be full. So we print out our hash table here, and now we see that those have been filled with llama and rooster. Now, if we try to add another item, perhaps fish, we will be unable to do so because our table is full, but we can remove an item. This time we can remove using del because we implemented the functionality for the del reserve keyword with our del item special method. And then we print again, and we see that lion is gone. Here's that empty slot. Just to test out a few other methods we implemented, we can print out the length of m using the built-in Python function len, which will say there are 10 items in our map, which makes sense because we made it have a size 11 and it was full, and then we removed 1. And just testing out our membership, is cow in m? Yes, it is. Here it is. Is fish in m? No, it's not. We were unable to insert it because our table was full. Here are some practice problems to work with related to hash tables and hash table implementations. I highly recommend working through these for extra practice, more than just what we had here in the lesson notes. Now I'm going to switch gears to talk about L8-3, which discusses the requirements for a hash function and a few different hash functions that are good to learn about. So let's talk about the requirements for a hash function in terms of what would make the perfect hash function. A hash function that maps each item to a unique slot is a perfect hash function. Unfortunately, given an arbitrary collection of items, there is no systematic way to construct a perfect hash function. Luckily, we do not need the hash function to be perfect to still gain performance efficiency. One way is to always have a perfect hash function is to increase the size of the hash table so that each possible value in the item range can be accommodated. This guarantees that each item will have a unique slot. Although this is practical for small numbers of items, it is not feasible when the number of possible items is large. For example, if the items were 9-digit social security numbers, this method would require almost 1 billion slots. If we only want to store data for a class of 25 students, we'll be wasting an enormous amount of memory. So here are some extensions to the remainder method that minimize the number of collisions, with the goal to minimize the number of collisions, be easy to compute, and evenly distribute the items in the hash table. So let's talk about the folding method. The folding method begins by dividing the item into equal size pieces, and the last piece may not be of equal size. These pieces are then added together to give the resulting hash value. As an example, if our item was the phone number 436-555-4601, we could take the digits and divide them into 2 groups of 2, After the addition, we get 210. If we assume our hash table has 11 slots, then we need to perform the extra step of dividing by 11 and keeping the remainder. In this case, 210 mod 11 is 1, so the phone number example would hash to the slot 1. Some folding methods go one step further and reverse every other piece before the addition. For the above example, we would get 43 plus 56, which is 65 reversed, 55, 64, which is 46 reversed, and 01, which is 219, which would give us a different slot of 10. Another method is the mid-square method. In the mid-square method, we first square the item and then extract some portion of the resulting digits. For example, if the item were 44, we would first compute 44 squared, which is this really large number, by extracting the middle two digits, 93, and performing the remainder step, we get 5. 93 mod 11, 93 mod 11. This table shows items under both the remainder method and the mid-square method. Let's return to how we can produce hash functions, hash values for strings. So as we saw in a previous example, the Unicode values of characters can be summed and used in conjunction with the remainder method as a hash function. Here was the example here, where anagrams map to the same slot. So to fix this, we could use the position of the character as a weight, so that in this way the order does matter. So here we're going to get different hash codes, mod by 11 to get different hash values. And this would be what the implementation would look like as a hash function iterating through each character in a string called item, and then adding the Unicode value for that character multiplied by a weight associated with its position. So run this code, and there's the 3 and 2. Here are some practice problems related to hash functions that I recommend that you work through for extra practice. And one thing that I do want to note that I noticed earlier was there was a typo in the mid-square method that I just fixed. 44 squared is 1,936. The middle two digits are 93, which is going to be the value we're going to use in the remainder method. If we mod 93 by 11, then we get 5, and 5 would be the slot associated with this item 44. Now, in this table, I've worked through a few examples. For example, if the item to insert is 54, 54 squared is 2,916. Grab the middle digits, which is 91, and then mod 91 by 11, which will give us 3. Please work through the remaining examples here so that you're comfortable with the mid-square method.